We will solve the problem 720, which says the oscillating fan shown in figure is to be analyzed as a double rocker. The fan housing is link 2, the motor shaft is connected to link 3, and link 4 is connected from the coupler to the frame. The actual input of the mechanism is the coupler. So this is a type 1 double rocker. It satisfies Grashof condition. The actual input of the mechanism is the coupler, and omega 3 with respect to link 2 is constant at 956 radian per second. In the counterclockwise direction, which is taken as positive, and we are supposed to compute the angular velocity and angular acceleration of link 2. Now, in order to solve this problem, we have to first do position analysis, then velocity analysis, and then acceleration analysis. So let us look at how we can solve this problem. The mechanism looks something like this. So you have a coupler, which is the smallest link, the link lengths given are 0.75 for the first link, 3.0 for link 2, 0.5 for link 3, and 3.0 for link 4. All of these are in inches. We have to first perform the position analysis. Also given is that the input is given to link 3. So link 3 is rotated at a particular angular velocity. And also given is we have to find the angular velocity of link 2 and angular acceleration of link 2. And this has to be found out for the configuration where theta 2 is 120 degrees. As is usual with solving problems on kinematics, we will have to do first position analysis. For position analysis, we will have to write the loop closure equations. So for writing the loop closure equation, I first define the axis x and the axis y. Next, I can define vectors along the link of the mechanism. And if I draw vectors like this, and I call this as r1 vector, this as r2 vector, this as r3 vector, and this as r4 vector. From the basic principle of vector addition, I can see that r1 vector plus r2 vector will be equal to r2 vector plus r3 vector will be equal to r1 vector plus r4 vector. So writing the loop closure equations, we have r1 vector plus r4 vector will be equal to r3 vector plus r2 vector, because they are reaching the same point, right? r2 vector plus r3 vector, because they are reaching the same point on the mechanism. Again, as a standard, if I break them down into two component equations along x and y, I will have r1 cos theta 1 plus r4 cos theta 4 is equal to r2 cos theta 2 plus r3 cos theta 3. And similarly, along y, r1 sin theta 1 plus r4 sin theta 4 is equal to r2 sin theta 2 plus r3 sin theta 3. Since I have to do velocity analysis, let us number these equations 1 and 2. For velocity analysis, if I take the derivative of these two equations, I will get the velocity equations. If I take the derivative of the first equation, I'll get r1 minus sine theta 1 dot plus r4 minus sine theta 4 dot, and I will also get r1 for equation 2 cos theta 1 dot, r4 cos theta 4 dot is equal to r2 cos theta 2 dot plus r3 cos theta 3 dot. Here these two terms will be 0 as theta 1 dot is 0. It is the fixed link. And from these two equations, I can get the velocity mappings in the matrix form. So in this matrix, it will be minus r2 sine theta 2, r4 sine theta 4, minus r2 cos theta 2, and r4 cos theta 4. This is equal to r3 sine theta 3 dot and r3 cos theta 3 dot. These are the velocity relations. I can also take another derivative to get the acceleration relation. Let us look first at how we can solve the velocity equations. In order to solve the velocity equations, if I look at the expressions that I have got here, in order to find out theta 2 dot and theta 4 dot, I need to know what is theta 2, theta 4, and also what is theta 3. Theta 3 dot is given to me. In order to calculate And if I look at the problem that I have got, theta 2 is already provided in the problem as 120 degrees, and theta 3 and theta 4 have to be computed. So this is a little variation of the problem, standard problem. So here for position analysis, theta 2 is given, theta 3 and theta 4 have to be computed. Whereas for the velocity analysis, theta 3 dot is given, and theta 2 dot and theta 4 dot have to be computed. Let us try to do the position analysis. We know that we already have the solution for the condition when theta 2 is known and theta 3 and theta 4 have to be computed. Theta 1 is known, theta 1 is 0 in this case. We already have a solution for this, and I assume that in the problem the solution is given in the problem, in the question paper itself. If it is not given, then there will be more marks in the problem for computing these relations, for deriving these relations. But assuming that we have either derived it or it is given in the problem statement itself, I can have the following relations. So when I want to do the kinematics, I first can calculate the terms A, B, and C. The term A is this 2r1 r4 cos theta 1 minus 2r2 r4 cos theta 2. In our case, this will be 2 into 0.75 multiplied by 3 into cos theta 1 is 1 because theta 1 is 0, minus 2 into 3 into 3, r2 is 3, r4 is 3, cos of 120 degrees, and this comes out to be 13.5. Similarly, B can be computed as 2 into r1 r4 sine theta 1 minus 2 into r2 r4 sine theta 2, and then since sine theta 1 is 0, I am left with only the second term, which is 2 into r2 r4 sine of 120 degrees. This will come out to be minus 9 root 3. C can be calculated as r1 square plus r2 square plus r4 square minus r3 square minus 2 r1 r2 cos theta 1 cos theta 2 plus sin theta 1 sin theta 2. These expressions, as I said, either you derive it and then you have to spend time for that, or if it is given you can directly use it. 0.75 square plus 3 square plus 3 square minus 0.5 square minus 2 into 0.75 into 3. Cos theta 1 is 1, cos theta 2 is cos of 120 degrees, and the answer is 20.5625. From this, I can calculate the value of t, which is equal to minus of 9 root 3 plus minus 9 root 3 square minus 20.5625 square plus 13.5 square. 20.5625 minus 13.5. So this is the standard formula that we have, which says that t is minus b plus minus b square minus c square plus a square divided by c minus a. So with this, I get t is equal to, I get two values of t. So for t is equal to, I get either 2.4281 with positive sign here, and t is equal to uh, so I can calculate this. T is equal to 1.9863 with negative sign. And based on this, I get theta 4 is equal to 135.23 degrees, or theta 4 is equal to 126.55 degrees. I get two solutions. Which solution should I accept? In this particular problem, it is not very obvious which solution we should accept, but we can draw a simple drawing. If we have a tool for measuring the angles, I can draw the second link like this at 120 degrees, and then I can draw the two configurations of for the two values of theta 4. In one of the configurations, this larger angle, I will find that it is crossing the link 2. Link 4 is crossing the link 2, and this is not what is shown in the diagram given in the problem. So I reject this solution and I accept this solution based on how the mechanism is visually represented in the problem itself. And after this, I have the expression for sine theta 3, which is r1 sine theta 1 plus r4 sine theta 4 minus r2 sine theta 2 divided by r3. If I plug in the values, it is 0.75 into 0 plus 3 into sine of 126.55 degrees minus r2 is 3 and theta 2 is 120 degrees divided by r3. So r3 is 0.5. What I get here is minus 0.37613. This is the value of sine theta 3. Similarly, the value of cos theta 3 I can also compute as r1 cos theta 1 plus r4 cos theta 4 minus r2 cos theta 2 divided by r3, and this is 0.75 3 into sine of cos of 126.55 degrees minus 3 times cos of 120 degrees divided by 0.5, and this comes out to be 0.9268. Once I have computed this, I will have to calculate the angle theta 3 using the two argument tan inverse. So theta 3 is equal to a tan 2 sine theta 3 comma cos theta 3. So a tan 2 is indicative of 2 argument tan inverse. So based on the values I have computed, it is minus 0.37613 comma 0.9268. Now, since I am doing a 4 quadrant tan inverse, I can have a basic check to see which quadrant does this lie in. So I'll find that this lies in the 4th quadrant where sine is negative and cos is positive. If I have a standard calculator, it will automatically give me a solution either in 1st quadrant or 4th quadrant. So I don't have to do anything else. If I just do tan inverse of this ratio, I will get the value of theta 3. So theta 3 comes out to be minus 22.08 degrees. Once I have this, I can put these values back into the equation for velocity. This is the equation for velocity. Let us call it equation number 3. And I can put these values back into equation number 3 to get the velocities. So if I put the values in equation number 3, it is minus 3 sine 120 degrees, minus 3 cos 120 degrees, 3 sine 126.55 degrees, 3 cos 126.55 degrees multiplied by theta 2 dot and theta 4 dot, and this should be equal to 0.5 into sine theta 3. Sine theta 3 is this 37613 and multiplied by theta 3 dot, which is 956. So theta 3 dot is given to be 956 radian per second. Similarly here 0.9268 into 956, and then you can enter these matrices in a calculator that is capable of doing matrix calculation, and then what you get is theta 2 dot is equal to minus 727.0886 radian per second, and theta 4 dot is equal to minus 858.4278 radian per second. This solution also makes sense if you look at this visually. If I am rotating link 3 in anti-clockwise direction, I would expect that link 2 and link 4 will move in clockwise direction. So clockwise rotations are negative by convention and anti-clockwise rotations are positive. So that's why here I took theta 3 dot as 956 because it's an anti-clockwise rotation which is positive, and theta 2 dot and theta 4 dot are coming out to be negative, which means clockwise rotation. So this is velocity analysis. Can you similarly find out acceleration of link 2? So you'll have to differentiate, take time derivative of the velocity equation, come up with the acceleration equations. Acceleration equations will have terms of theta 2 dot square and theta 3 double dot, and based on that you will be able to calculate theta 2 double dot and theta 4 double dot.